Hi guys, welcome back. We're starting notes for sections 10.4 to 10.6, so we're really going to pick up just right where we left off. Again, this is where I'd like you to pause if you don't have a piece of paper out. You're going to get paper out for the U tries. So there'll be 3 U tries in this particular video. So you'll do those throughout, and you'll submit it to Canvas as soon as you have it done. Okay, so we'll get started here. So we finished talking about ionic bonds and how to draw Lewis structures for ionic bonds in our last video. Now we're going to talk about covalent bonds, so what covalent bonds are and how we draw the Lewis structures for those. So just a reminder, a covalent bond is when a nonmetal is bonded together with another nonmetal. So anytime 2 nonmetals make up a compound, they're forming a covalent bond. And the difference between a covalent bond and an ionic bond, in an ionic bond, there was a transferring of electrons. In a covalent bond, you're going to get a shared electron. So those electrons are going to, or there's 2 elements are going to come together and share those electrons in order to try to obtain an octet, to get the most stable compound that you can. So let's look at an example of what this will look like, especially if we're drawing the Lewis structure for it. So what I'm going to give you here, and let me get a pen going, is hydrogen and oxygen. And hydrogen and oxygen are both nonmetals, which makes this a covalent compound. So we can immediately identify that. And the first step, like we've been doing, is to first look at how many valence electrons each of these has. Hydrogen is an easy one. It only has 1 valence electron. And oxygen has a total of 1, 2, 3, 4, 5, 6 valence electrons. And in case you forgot, we're identifying valence electrons either by doing the electron configurations or by looking at the periodic table. So for oxygen, I just looked at the periodic table and looked at what column it was in, and it was in column 6, which made it have 6 valence electrons. So if I were to bond this together, hydrogen and oxygen. So remember, hydrogen is a diatom, just as a reminder. And a diatom means it exists as 2 always in nature. So we look at those as Brinkelhoff, and hydrogen is one of those ones, the H in Hoff. So we know actually when we're bonding these together, we actually have H2 here. And H2 with 1 oxygen gives you H2O. So that's actually the compound that we'll be drawing the Lewis structure for. Now hydrogen, like we said, has 1 valence electron and oxygen has 2. And you'll note this actually is perfect because oxygen needs an octet. Hydrogen is okay with a duet. So when I bond 2 hydrogens on either side of my oxygen, I've created a full octet for oxygen because my 1 hydrogen and my 1 hydrogen bring in enough valence electrons to fulfill oxygen 6 and give it 8. And then each hydrogen has its 2 valence electrons, making it a perfect duet. So actually every element in this compound is now stable. So I've identified here in yellow, this is the octet that oxygen has, 2, 4, 6, 8, and hydrogen has the 2. Now, something important to note when you're looking at these. The hydrogen bonded to the oxygen, this set of valence electrons, this bond is called the bonding pair because the hydrogen and the oxygen are actually sharing these 2 electrons, and it's almost like you're double counting it because I count this as hydrogen having 2 and I also count this as oxygen having 2. Now this pair, the pair that isn't attached to the hydrogen but is attached to the oxygen, those are called lone pairs. Lone pairs mean they are contributing to the octet of the oxygen here, but they are not shared with another element. Now notice how I wrote this. I wrote this with 2 electrons, or 2 dots representing the electrons. You can also represent a bonding pair as a dash. So I've written this for you here. If a hydrogen is bonded to an oxygen, the dash is going to be representative of those 2 dots. So if you like this format better, you're more than welcome to do this. In fact, most of the time in the examples I'll do, I will use the dash as my bonding pair and use the 2 dots as my lone pair. It's also a good way to determine if electrons are being shared between 2 elements. Okay, So I actually mentioned this on the previous slide, but just a reminder for you that Brinkelhoff means that something exists as a diatom, and that means that it exists in sets of two. So we've got bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So just like you saw in the last example, if you have one of these elements, really you have two. And what's interesting about Lewis models is it actually explains why they exist as diatoms in nature. It's a really good example. So if we look at chlorine, which has 7 valence electrons, we're one short of having that octet. If two chlorines bond together, and I drew the two examples here for you, the one with the 2 dots as the bonding pair and the one with the dash as the bonding pair, you'll see that they each have an octet if they sit close together. So that's why these always exist in nature together. They're much happier and they're much more stable when they're paired together. So puts a little bit of reasoning behind Brinkelhoff, which is something we've been saying all year. Okay, so the next thing is double and triple bonds. So this is where things get sort of fancy here. So we can draw Lewis structures, but sometimes what you'll notice is that you'll have not quite enough valence electrons to go all the way around without creating a double or a triple bond. So let's look at this example. So if I wanted you to draw the Lewis structure for oxygen or O2, so remember oxygen is Brinkelhoff, it's a diatom, so it's going to exist as 2. Oxygen itself has 2, 4, 5, 6 valence electrons, so it's going to have a total of 12 valence electrons. So if I have a total of 12 valence electrons, I need to distribute those evenly amongst all of these. So if I go all the way around, I've got 2, 4, 6, 8, 10, 11, 12. But you'll notice this doesn't work because each oxygen does not have an octet. This one is a solo and this one is a solo electron. So each one actually only has 7 valence electrons. Now, if I do this, I can write it this way as well, and I can put those 2 on maybe say this oxygen, but then this oxygen still does not have an octet. So this example does not work. So we have to use a double bond here. So the way that you do this is you are going to take one of the lone pairs and you are going to force it to become a bonding pair. So in this case, I'm going to take one of my lone pairs, maybe perhaps this one, and I'm going to bring it to the center. So the way I would draw this is I would say I have 4 electrons that are being shared, and I need to get to 12. So I have 4, 6, 8, 10, 12. I have now used all 12 valence electrons, and each element has an octet. So 1, 2, 3, 4, 5, 6, 7, 8 around this oxygen, and 1, 2, 3, 4, 5, 6, 7, 8. So remember earlier I said when you have this shared or bonded pair, you actually count it twice. This counts for 2 towards this oxygen, and it also counts for 2 towards this oxygen. So if you are struggling to find an octet for each element as you're bonding 2 elements together, then it may be because you need a double bond. You need to take a lone pair and create it or convert it into a shared or bonded pair. And that's what we needed to do here. And remember, I told you could really do it either of these ways. You can have the dashes, or if you like the dot method better because it's easier for you to count, which I understand, you can draw it this way, and that would be acceptable as well. And I've outlined here where the octet is, right? 1, 2, 3, 4, 5, 6, 7, 8 around our blue oxygen. And then again, you double count 1, 2, 3, 4, 5, 6, 7, and 8 around our pink oxygen here. So that's how we're counting. Now each oxygen has its octet, and they're both stable and they're both happy. Okay. So just a reminder, a double bond is when 2 electron pairs are shared between 2 atoms. So you no longer have a lone pair, you take a lone pair and convert it into a bonding pair. Now double bonds are shorter in length, but they're much stronger, which makes sense. Okay, now you can also have a triple bond. So a triple bond is even shorter and stronger than a double bond. So we'll look at an example of something that has a triple bond. So if I want to bond together two nitrogens, or N2, again, nitrogen is a Brinkelhoff, I'm going to have these two nitrogens, 10 valence electrons, because each nitrogen has 5 valence electrons, so 10 total. And I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But of course, each of these are missing 2 valence electrons to fulfill their octet. So what we're going to do is draw or add a lone pair, and one lone pair won't be enough. We're going to have to drag 2 lone pairs to the center. So if I drag 2 lone pairs to the center, I still have 2, 4, 6, 8, 10 total valence electrons, and I have that triple bond in the center. And now each nitrogen has an octet, and it's happy. So these are kind of tricky. You kind of have to get crafty when you're dealing with double and triple bonds, because you want to make sure that you, one, have the correct valence electron count, but you also have to make sure everything's happy, everything has that octet. So you kind of have to get a little bit crafty in moving valence electrons around to try to make sure everything gets that stability that it wants. Okay, so what are the steps for writing Lewis structures for covalent compounds? So there's kind of 4 big steps here. So the first step is to write out the correct skeletal structure for the compound. So what does that look like? So a skeletal structure basically says, okay, if I tell you I want the skeletal structure for H2O, the skeletal structure is going to be me going, okay, well, I've got 2 hydrogens and 1 oxygen, so it's probably going to look something like this. That's the skeletal structure. There's no valence electrons around it. There's nothing other than this is going to be what the general shape is going to look like. And that's all the skeletal structure says. It's how everything's going to line up. And something that I like to remember is that hydrogens are always going to be on the end. Because remember, hydrogens only exist as duets, or only want duets. They don't need an octet. So it's never going to be a hydrogen that's your central atom. It's always going to be something else. So if you have H2O, you can always start with oxygen in the middle and place those 2 hydrogens so that they're on the outside. Okay? Then you're going to calculate the total number of electrons for a Lewis structure by summing the valence electrons for each atom in the molecule. Now, we've been doing this the whole time. So hydrogen has 1 valence electron, and oxygen, if I go to my periodic table, which is what you guys will do, it says oxygen has 6 valence electrons. So I know I have 6 valence electrons here. And hydrogen has 1 valence electron. So in this case, 6, 7, 8 total valence electrons. So you're going to total your valence electrons up. That's step 2, total valence electron count. Step 3 is to distribute the electrons among the atoms and giving everything an octet to as many as possible. So in this case, I draw this outline, and this is where I'm going to distribute my valence electrons. So I needed 8, and I have 2, 4, 6, 8. Oxygen has its octet, and each hydrogen has its duet. So this is happy. And then if any atoms lack an octet, form double or triple bonds as necessary to give them octets. So your third step will be, if something didn't have an octet or a duet, to give it a double or triple bond and make it stable. Okay? Okay, so we're on our first U try. So you're going to draw the Lewis structures for CO2 and CCl4. Now, it'll be helpful to use those steps. So remember, as we're doing this, the first thing you're going to do, skeletal structure for each of these. Then you're going to total your valence electrons. And then you're going to draw Lewis diagram or structure. And then you're going to double check that everything has an octet. Okay, so those are your steps. So for CO2 and CL4, pause, and then we'll go over the answers. Okay, so let's look at CO2 first. So the first thing I did was say carbon has 4 valence electrons, oxygen has 6 valence electrons, but I have 2 of them, so I have 12 valence electrons total for oxygen. I'm going to tally up my 12 plus 4 valence electrons from carbon, and that's going to give me a total of 16 valence electrons, which means for my Lewis structure, I need to have 16 total valence electrons around my Lewis structure. The next thing I'm going to do, draw my skeletal structure. So oxygen, I know I have 2 of those and 1 carbon. So just to make it look even, I'm going to have an oxygen on either side of my carbon. And I know that those will be bonded together. So now I need to distribute my 16 valence electrons around my Lewis diagram. So I'm going to start out, and I'll actually do this for you here. So I've got 4 already. So I've got 4, 6, 8, 10, 12, 14, 16. So I've now run out of valence electrons to go around, and this oxygen has not met its octet. So we're going to have to double bond. So what I am going to do is use one of these to create a double bond here. And I'm going to use another one of these to create a double bond here. So if I rewrite this, I'm going to have 2 of my lone pairs. So I've used 1, 2, 3, 4, or 2, 4, 6, 8, 10, 12, 14, 16. That's a total of 16 valence electrons. Carbon has its octet, 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. And this oxygen has 2, 4, 6, 8. So each has met its octet. We had to use double bonds to get there, but everything is happy. So again, you can choose where you want to put these dots around your oxygen. You could have 2 on the top, 2 on the side. You can use the bottom. It doesn't really matter. But that's your final answer. Now for CCl4, this is a shape we haven't seen before. So we've got 1 carbon and 4 chlorines. So the way we would orient this is having a carbon in the middle surrounded by a chlorine on each side of that carbon. That's going to be your skeletal structure. Now as we count our valence electrons, carbon has 4 valence electrons and chlorine has 7 valence electrons, but we have 4 of them. We know that because the subscript says 4. So that makes 28 valence electrons from chlorine. We add that to our 4 valence electrons from carbon, and we get 32 valence electrons total. So we need to distribute 32 valence electrons around our Lewis structure. So in this case, I drew the diagram this time using the dots instead of the dashes for the shared pairs of electrons, but you can do the dashes and that's fine. And we'll count. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And everyone is happy because everybody has an octet. So this one actually was slightly easier than that last one. There was no double bonds needed. Okay. Next big idea here is polyatomic ions. So writing Lewis structures for polyatomic ions. We know what polyatomic ions are. Ions are things that have a charge, either a positive or a negative charge. So what you need to do when thinking about polyatomic ions or anything that has a charge is it's going to affect your total valence electron count. So if you have an overall negative charge, then you're going to add an electron. If you have an overall positive charge, then you're going to subtract 1 electron. And we'll look at what this means. And we'll use bracket notation with whatever the overall charge is. So let's take a look at how we would draw this. So here's an example. If I gave you CN- or cyanide, cyanide has an overall minus charge. And on this last slide, I told you if it has a negative charge, you're going to add 1 electron to your total count. So cyanide has an overall negative charge, so I'm going to add 1 valence electron to my total valence electron count. So carbon has 4 valence electrons, nitrogen has 5 valence electrons. I have the minus sign, so I have to add this 1 additional valence electron, and that's going to give me a total of 10 valence electrons for my cyanide Lewis structure. Now, if I draw my skeletal structure, it's going to be a C bonded to an N. So I know there's going to be some shared pair of valence electrons here. And I have to find a way to distribute 10 around there. So if I distribute my 10, 2, 4, 6, 8, 10, nitrogen does not have an octet. It only has 4 around it. So we have to find a way to move this lone pair to become a bonded pair between carbon and nitrogen. So if I move that lone pair, I end up with a double bond, and I have 2, 4, 6, 8 total, 10 total, but I still don't have an octet. I only have 2, 4, 6, 8 around carbon and 2, 4, 6 around nitrogen. So nitrogen still is not complete. So I have to do one more transfer. I have to bring another pair to make this a triple bond. So I bring one more shared pair, and now I have 2, 4, 6, 8, 10 total valence electrons, and I have 2, 4, 6, 8 around carbon and 2, 4, 6, 8 around nitrogen. And again, if you wanted to do it with the dot model, you can do it that way, or you can use your dashes. Okay. Oh, I almost forgot. The last thing you need to do is put brackets around this, saying that this has an overall minus charge. So whatever this charge is, you're going to put brackets around your final answer, and you'll put the overall charge there. Okay, let's do a U try. So you're going to do one for a polyatomic ion, NH4 plus, so this is different. On the last one it was a minus. This means you're going to subtract 1 valence electron. And this one has an overall minus charge, which means you're going to add overall 1 valence electron. And these are going to be the same steps that you're going to take on these. So the first one is going to be draw your skeletal structure. Then after that, you're going to sum up your valence electrons, so you know how many you have to do. And then finally, you're going to draw your Lewis structure. Okay, so go ahead and pause, give this a go, and then we'll go over the answers. Okay, so let's look at NH4 plus. So remember, it has an overall positive charge, so we're going to subtract 1 valence electron. So nitrogen has 5 valence electrons, hydrogen has 1, but we have 4 of them, so we have 4 valence electrons from that. And then we're going to subtract our 1 valence electron. So 5 plus 4 minus 1 gives us a total of 8 valence electrons. So our final Lewis structure has to have a total of 8 valence electrons around it. Now, if we were going to draw the skeletal structure for this, remember hydrogens, as I said, only want duets, so they always need to be on the outside, which means nitrogen should be our central atom. So I'll start with nitrogen, and I know my 4 hydrogens are going to bond off of each side of this nitrogen. So that's my skeletal structure. Now I have to distribute my 8 valence electrons, and actually I've already done it. 2, 4, 6, 8. They're all surrounding the bonding of the hydrogen to the nitrogen, gives that nitrogen its full octet, and then each hydrogen is happy with its duet. Now remember the last step, put the brackets around. This has an overall 1 plus charge, so you would put a positive charge up here. And down here I wrote the 2 formats. So again, here's the dot version versus the dash version. Either of these are acceptable, just don't forget the brackets for charge. Okay, now this next example, ClO minus, this has an overall minus charge, so we're going to add 1 total valence electron to this count. So chlorine has 7 valence electrons, oxygen has 6 valence electrons, plus that 1 additional from the minus charge gives us a total of 14 valence electrons. I just have a Cl and an O, so my skeletal structure will probably look something like this. And as I distribute those 14 valence electrons, it actually works out very nicely. 2, 4, 6, 8, 10, 12, 14, each has an octet. The only thing you have to remember to do, again, is put that overall minus charge up at the top. And again, here's both versions, the dash versus the dot. Okay. This is the last big idea for Lewis structures, and that's resonance structures. So resonance structures are basically looking at alternatives to writing Lewis structures. So some Lewis structures, even though you've written it the correct way, have an additional way that they can be written where it's still correct, where it can still have an octet. It still uses all the same valence electrons, but it will have a slightly different shape. So we'll look at how that works. So let's look at SO2, for example. So SO2, I did my total valence count here. Sulfur has 6 valence electrons. Oxygen has 6, but we have 2 of them, so that's 12 total valence electrons plus 6 gives us a total of 18 valence electrons. Here's my skeletal structure. I have 2 O's on either side of my S. And then I have to distribute my valence electrons. So I have 18 to give out. It turns out this one's going to need a double bond in order for sulfur to get its octet. This one has one, but this one does not. So we do a double bond on only one side. This side has it, this side does not. So we actually end up with a structure like this, with a double bond on one side, but not on the other side. So we haven't actually seen this before. So what resonance means is there's another way I can write this where this is actually still correct. And that's by moving the double bond to the other side of the S. So see how the double bond is on the left, to the left of the S, and on this one, the double bond is to the right of the S. That's considered a resonance structure. So if I were the Lewis structures for SO2, there are 2 ways that it works. And these are the 2 Lewis, or the 2 resonance structures, or the 2 Lewis structures that work for SO2. So in some cases, it may ask you to just draw the Lewis structure, and if you give this as an answer, that's fine. But in some questions, it'll say, if there's a resonance structure, make sure that you draw it. And in this case, there would be a resonance structure, so you would have to draw both of these in order to have the answer correct. Now, obviously, if this had a double bond here, there would be no resonance for this structure. You're already even. If you're not even, then you have to draw a resonance structure. Okay, this is your last U try. So on here, you are going to do, and note that these all have a charge. So remember here, you're going to be adding plus 1 valence electron, and here you're going to be subtracting 1 valence electron from your total answer, and you'll also need brackets around your final answer. And again, same steps. So draw the skeletal structure. You're going to sum up the total number of valence electrons, and then you're going to draw the Lewis structure and ensure that everything has an octet. So go ahead and pause here and work through that, and we'll go over the answers. Okay, so this first one is NO3 with an overall minus charge, which means we're going to be adding 1 valence electron. So nitrogen has 5 valence electrons, oxygen has 6 valence electrons, but there are 3 of them. So that gives us a total of 18, plus that 1 valence electron from the negative charge, plus our 5 from our nitrogen, gives us a total of 24 valence electrons. Here's our skeletal structure. Nitrogen's going to be in the middle because we have 1 of them, and we'll put those O's surrounding the nitrogen. So I've gone ahead and drawn out each of the 3 resonance structures here. So if you were able to get to one of these, you were able to draw a Lewis structure and you realized it needed 1 double bond on some side of this, then this would be correct. But you should know there's 3 possible resonance structures here because that double bond can be in 3 different places, right? It could be to the right, it could be to the left, or it could be on the top, or potentially, depending on how you drew this, it could have been on the bottom too if you chose to draw your Lewis structure in this orientation, which would have been fine as well, like this. Okay. So that's it for NO3. And for NO2 minus, so with this, we're going to be adding a valence electron, so plus 1 valence electron. We have 5 for nitrogen, 6 for oxygen, only 2 instead of 3 here, so we have a total of 18 valence electrons. There are only 2 possible skeletal structures here, and it's a similar situation. The double bond can either be to the right of the nitrogen or to the left of the nitrogen. Okay? So this is actually the end of our Lewis structures lesson. So if you missed something on here, 1, you can always replay this video, or 2, we'll be going over this in class. Now there is a homework assignment associated with this. It's writing Lewis structures for polyatomic ions, and it asks you to go through all of these steps. That's been posted to your Canvas page. So following this and following submitting your U-tries onto your Canvas submission page, you will be completing that assignment and also uploading that to Canvas. And then we'll spend some time going over that in class together if you guys have questions. So enjoy the rest of your day, and we'll talk soon. All right.